Hello everyone, welcome to another physical sciences lesson, and we're continuing looking at electrochemistry. And today we're going to focus on the applications of the electrolytic cell. So let's go to it straight away. So as we look at the electrolytic cell, here's a question for you to think about. When are electrolytic cells used? You know what, in science, we don't just want to have a whole bunch of theory, we want something that's practical and something that is useful for society and can make our lives easier. Science isn't just about dusty textbooks, it's about observation, it's about engaging, it's about critical thinking, and it's about the link between science and technology. And so that's our area of focus today. Where and when do you think we would use electrolytic cells? Well, let's move on and look at our concept map so we can remind ourselves of the key features. So when we look at electrolytic cells, remember that they, just like the galvanic cell, they have an anode and a cathode. And as I've said, we're going to be looking at the applications of that. But just to remind you, the way we tell the anode is that's where oxidation takes place. So we get oxidation at the anode, remember an-ox. And when we look for the cathode, we're looking for the cat, and we're saying it's the red cat. So with that in mind, let's go and look at one simple application, which you have seen before, the electrolysis of copper chloride. Now, do you remember that when we use electrolysis, we've got a solution of copper chloride. The ions have dissolved and they've dissociated. So we've got them running around in the water, and that has become an electrolyte. And onto the one half cell, onto the one electrode, we're going to get a plating of copper, and onto the other one, we're going to get bubbles of chlorine gas. So we've gone through that, and it is an application of the electrolytic cell. I'm not going to dive into it in too much more detail because I know that you're very familiar with this. But it is a general principle that you can take a compound and separate it into its elements. And we can do this not only in a small scale in a school laboratory or in a university laboratory even, but we can do it on a massive scale in industry. And probably the most famous of these electrolytic cells is found in the use and the recycling of aluminium. So we're not going to focus too much on this, but I just want to get you the principle. We can extract aluminium from the rock that contains aluminium. We call that rock bauxite, and it is aluminium oxide. Let's just go and have a look at exactly what's happening here. So we're looking at the extraction of metals, that's the element, from the ore, which is usually a compound. Now, I've mentioned the word electrolyte, which is usually a solution. But in this case, we don't use a solution, we use a pure liquid. In other words, we take the aluminium oxide and we melt it. And it gets melted at a very high temperature, furnace-type temperatures, over 1,000 degrees Celsius. And those are usually electric furnaces as well, that then bring in this molten mixture. And the reason I'm saying it's a mixture, because they do something special. Have a look at the diagram to explain it, so you can see what's going on. Now, this diagram isn't particularly colorful, a little bit gray, but this area here, these dotted lines over here, that represents the molten mixture of aluminium oxide. But within that mixture, there's something called cryolite. The formula for cryolite is Na3Al F6. You don't need to remember that, but you do need to know the function of why it's there, because it's also got some aluminium in it, and it's a mineral. Comes from some of the rocks. They melt it, they purify it, they make sure that the aluminium oxide is pure, that the cryolite is pure, and then they mix it together. And the reason that they use the cryolite is to lower the melting point of this molten mixture, which in a way is also an electrolyte, because the ions are separated in the molten liquid. And so the positive ions can go in one direction, the negative ions can go in another direction. The cryolite helps to keep the melting point of the mixture low because it melts before the aluminium. And because of that, the whole mixture gets melted a lot quicker. Okay, so now let's see. We've got some ions in the solution. Just let's have a look at the structure. So this cell has got an outer layer, which I've just outlined there, and that's the, I've gone over, so let's just do that again. Outline the metal part on the outside there, and that's the steel case. Now, the steel isn't very good we don't want that to be exposed to electricity because that could be problematic. For anybody walking past, it could be electric. So some of it's insulated on the outside, but there's a steel case that can contain these very high temperatures of the molten liquid inside. But the actual electrode that we're going to use to extract the aluminium from is some graphite. Now, graphite is a particular form of carbon. It's like the pencil lead that you use to write with. It conducts electricity very well. And this graphite a lining is connected to the negative electrode of the power supply. So this is all negative. And I need you to recognize if that's negative, what's going to pull onto that surface? Well, all the little positive ions are going to be attracted to that. And remember, aluminium ions are 3+. So all the aluminium is going to be in touch with this. It runs down into a container at the bottom. Sometimes these are sloped, and we're getting pure aluminium, molten liquid aluminium, passing out of the cell into a collection vessel. We've got the pure aluminium, which they can then put into a cast, and they can roll it, and they can do all sorts of fancy things with it to make cans and foil and all the lovely things that we have with aluminium. It can even be included with steel to make alloys. So it's a very, very useful material because it has a low density. And that's why we really like to look at it. But what happens at the other electrode? And what else do you think is going to be produced? Well, have a look here. At this point over here is also a graphite electrode, but that is connected to the positive terminal. And as I said, if we had aluminium as the positive ions, with bauxite, we'd have oxide as the negative ion. So we're going to get oxide from the molten mixture coming in contact with the positive cell. There's going to be a reaction there, a redox reaction. Let's go and have a look and explore these reactions in a little bit more detail and explain how they're working. So aluminium oxide is going to produce aluminium and oxygen. There's the full balanced equation. So we've got Al2O3 giving us 2Al plus 3O2. Full reaction. We could use oxidation numbers to see what's actually happening. And I want you to make sure that you can do that. But I'm not going to do it for you. I'm just going to remind you. Please try it for yourself. Let's go and see what the half reactions might be. And so when we do the half reactions, we're going to look at our table of standard reduction potentials, and we're looking for either aluminium or oxide. And what we recognize is there's aluminium. We've got aluminium. We haven't actually got aluminium. We haven't got aluminium. We've got aluminium ions. So this isn't going to be the reducing agent. We recognize the aluminium ions are going to produce aluminium. So what is that? That's the reduction reaction. And so if we look over here, we can write the reduction reaction for the aluminium as aluminium 3 plus 3 electrons to give us 3 lots of aluminium. And in this case, these would be in the liquid form, and that would still be hot and liquid. But what's happening at the anode then? Well, that's the oxidation reaction. We're going to get the oxide ion that's going to lose electrons. So oxide, O2 minus, it's also in the liquid form. It's going to form O2 plus 2 electrons. Now I hope you can see there's an imbalance there. And we'd have to balance the equation if we were writing it as the net equation. So 2 and 3, we're going to multiply this by 3, the whole thing by 3, and that will give us 6. We multiply this by 2 to give us 6 over here. And now we can add them together and we get 3 oxide ions, which were in their liquid form, plus 2 aluminiums in their ionic form that were liquid. And that's going to give us oxygen gas plus 6 lots of aluminium. Well, that's quite productive. And it's quite interesting that that gets going. But you know what? There's a problem. This is happening at extremely high temperatures. So the last thing I want you to recognize on this diagram is that if we're getting oxygen being produced here and we've got carbon over there, oxygen loves to react. It doesn't stay as it wants to. It reacts with carbon to produce carbon dioxide. So this is a problem for this particular process because the overall reaction isn't that. The overall reaction is that the oxygen then reacts with the carbon to produce carbon dioxide. And so we'd recognize that you're probably going to get 3 CO2 there because the graphite electrodes start wearing down because there's this continual reaction. So there's an example of an industrial process that is another example of using an electrolytic cell. So guys, the problem with this uses lots of electricity, contributes to greenhouse gases because of the intense electric furnaces that are being used, and it produces carbon dioxide. So really not a good idea to do so much extraction of aluminium from bauxite. Much preferable to recycle. You can use less aluminium. It's less environmentally friendly. It's more environmentally friendly, less hazardous, less carbon dioxide, and so recycle your aluminium cans wherever you can. For the moment, let's take a short break, and we'll be back to look at some more applications of electrolytic cells. Hello everyone, let's go and have a look at the next applications of electrolytic cells. And there are 2 of them that we want to discuss, and that is electroplating and something called electro refining. It's sometimes even called electro winning. It's just getting back stuff, making it purer. Electro refining, it's a process of getting the percentage of the metal purer, the less impurities. But let's start with electroplating, because this has become quite popular. A lot of people, when minerals were first extracted, wanted to have very high quality, very expensive cutlery. So the silver cutlery was the thing in the old days. You would bring out the good silver for people when you were entertaining guests. And even jewelry, you'd want to have sterling silver. You'd want to have pure silver jewelry. But as time has gone by, these very precious metals become more and more expensive. And so we've replaced pure silver with stainless steel, or sometimes, in some cases, with electroplated utensils. So it's not 100% silver. Silver itself isn't particularly hard and not particularly strong. It can break quite easily and it can tarnish. So what we do is we use a base metal to cover it. We've even been doing this with coins. You take nickel and you cover it with silver, and that's been going for a long time. But this process of not just painting on another layer of paint, but rather plating on another layer of metals. And that's what we're going to be looking at in this little segment. And it's quite interesting because what we've got here is a solution of silver nitrate. And we've got an electrode that's silver. And here the spoon could be any metal, but I've chosen to make the spoon zinc. And so we've got to look and see what's happening. in terms of this process, because we're wanting to get silver deposited onto the spoon. So we want to take this silver electrode, it's going to break apart, and so there's a reaction here, and there's another reaction there. In this first reaction, we're going from silver metal is going to form silver ions. And on this side, we've got the silver ions that are going to form silver metal on top of the zinc. And that's what this is all about. So it's almost the same, it is the same reaction. It's the redox reaction, the oxidation at the one electrode and the reduction at the other. And remember, we have to be able to identify which is the anode and the cathode. So let's do just that as we look at this. Now remember, you must identify the anode as where oxidation is taking place. And oxidation is the loss of electrons. So if we start with the metal, silver, as the solid, it's going to be able to lose electrons to form the silver ions, and we're going to write that as the electron over there. So where do you think that's happening? Well, the only place that we've got silver that's producing silver ions is on this electrode. So this electrode is the anode. And notice that this is the positive electrode. So that's why I'm saying to you, don't learn the signs of the electrodes for anode and cathode. It doesn't work. What works and what helps you to understand it is look for where oxidation has taken place. So at the other electrode, where we've got this zinc spoon, what's happening there? Well, that's the cathode reaction. And we're taking the ions, the silver ions, they're depositing onto the silver spoon, and that is the reaction where we get the opposite reaction. This is a reduction reaction. And we're finding that it's the silver ions plus an electron is going to give you silver. So I'm sure you see that these two are the reverse of each other. The one is oxidation, and of the same elements, the same ions and atoms, we're getting the reverse reaction happening at the other electrode. So you must say to me, so what makes something do and undo? What's the secret of this? What drives the reaction? Well, the critical thing to recognize, it's the battery. And over here, there is a supply of electrons that's going to drive the cathodic reaction. And because we're wanting these ions are being used up, we want more ions into the solution, that drives that reaction. So the two work together to produce this plating of silver on the spoon. Now, if we didn't have the battery, well, what do you think would happen? Well, I know we've done this before, so let's just have a look at it and remind you of what would happen. Is in the solution, we've got a zinc spoon, and way down on the next slide, on this table of standard reduction tables, we've got a silver electrode. Which one is the better reducing agent? Well, clearly, this one has an E0 value of plus 0.8, whereas the zinc has got a value of minus 0.76. So zinc is the better reducing agent. So the spoon would start to corrode and deposit zinc ions into the solution, and we would get the silver depositing the silver ions depositing onto the zinc. And we've seen that by direct contact, not with zinc and silver, we did with copper and silver. So please be aware of that. So if we didn't have the battery, then what in fact would happen is you've got a direct transfer of electrons between the zinc, and the zinc would be going to zinc ions, and the silver would be depositing on, and this silver here would just be ignored. Nothing would really happen. And that's not what we want. If this direct transfer was taking place, then we would have a galvanic cell, and it would have an E0 value. If we went back to it, the cathode was 0.8, and the anode, which was the zinc value, let me just pick up the zinc value. I think it was minus 0.76. I'm right, minus 0.76. And when you add those together, then you're going to get a value of 1,54, if I remember correctly, or I can do it, volts. So this is a particular challenge to us. If we don't have the battery on, we're going to get a galvanic cell or a direct transfer. So this also helps us to recognize that to make sure that that direct transfer doesn't happen, we must make sure that we have a potential difference between the silver spoon, the zinc spoon, and the silver electrode of more than this value. If we were to calculate for the electrolytic cell, you'd need to recognize that you're going to need a higher voltage than 1.56. If you do the calculation, you'll see it's naught, because at the anode, we've got silver going to silver ions plus an electron, and that was 0.8 plus 0.8. And over here, you've got, so that if we do the calculation, it doesn't look like you need any potential difference. But you've got to have a potential difference to undo that direct reaction. And so a voltage of the cell would have to be, the E0 of the cell would have to be greater than 1,56 volts. And remember, when we'd measure it, it would be negative because it's not spontaneous. We've got to oppose the galvanic reaction. So that's the important thing there. Right, let's move on to electrorefining. And electrorefining is where we take pure copper, which we've done from a previous process, and we take impure copper and we put them into a solution of, say, copper ions. Okay? It could be copper nitrate, it could be copper sulfate, doesn't really matter. How this is connected is that this is connected to the positive terminal, this is connected to the negative terminal. So what's happening here is that copper metal is going to form copper ions plus 2 electrons. So at the positive terminal, we're getting reduction, so this is the cathode. And at this electrode, we're getting electrons being added to the copper, so we're getting a different reaction here. You're getting copper 2 plus 2 electrons to form your copper, which is pure. And that's the principle of electrorefining. It seems strange. You've got impure copper on the one side, pure copper on the other side, and you're getting a bigger and bigger volume of pure copper. The impurities that are in the metal, those are deposited and they land, and they don't interfere because you're using an appropriate E0 for the battery. If you use an E0 that's too high, some of those could start to deposit, but we make sure that our potential difference in the battery is not big enough. Let's just make absolutely sure that we've got the identification of the anode and the cathode. And we just go back to that very quickly. Remember, the impure is where reduction has taken place, and reduction is at the cathode. So we're going to say copper is going to go to copper 2 plus 2 electrons. And over here, we've got copper 2 plus 2 electrons going to our pure copper. So guys, I want you to make sure that you can write the net reaction for this particular equation as well. So when we write the net equation, you'll see that on this side you've got copper 2 plus copper, and on this side we've got copper plus copper 2 plus. The electrons will cancel out, but your overall net reaction doesn't look like much has changed, but there's a significant increase in the In the anode, that's where you're going to get a bigger anode and a smaller cathode. So this will get less and less, your cathode will get smaller, and your anode will get bigger. This gets smaller, and this one gets bigger. Hello everyone, we're ready to get into some more investigation around the electrolytic cells. And in particular, we want to focus on one particular type of industry. That industry is known as the chlor-alkali industry. So let's get into that and make sure that we're understanding it's the most important application that we've got of this particular topic. So in our terminology, we're going to talk about the chlor-alkali industry. So this is a major industry because it's producing chlorine and it's also producing alkali. Now the alkali that we usually talk about here is something called sodium hydroxide. The other name for sodium hydroxide is called caustic soda. The formula for that is NaOH. So let me write that down so you don't forget that. Both of these products are extremely useful and they have lots of applications, both in industry. For example, chlorine is used not just to make bombs, as that was one of the first things that they did. Chlorine gas in the First World War was hugely destructive and it's very painful and led to the death of lots of people. Something that's actually been curtailed and restricted, the use of chemical weapons, although it unfortunately still does happen in certain conflicts. But chlorine has been used in other types of explosives as well. It's been used mainly, though, in the plastics industry. So you think about things like PVC. PVC, the C, polyvinyl chloride, hydrochloric acid, it all comes from chlorine. If we didn't have the chlorine, we wouldn't be able to make some of these very important things that we use all over the place. Not only plastics, even in some of your polyesters, you might find a chlorine or so thrown in. Drugs also have chlorine as one of their components. So it's very, very important, and it's a crucial industry. You can almost tell the industrialization of a country by looking at its production of sulfuric acid as well as the production of these particular products, chlorine and sodium hydroxide. Sodium hydroxide, its most common use that might be known around the house is as drain cleaner. It's very soluble. It's a soluble base, so we call it an alkali, but it's also very corrosive. And it can corrode, if it gets on your skin, it can corrode all the way through your bones. It's not a very nice chemical. You need absolute extra protection when you're working with it. But it's used in a number of production processes for fertilizers as well as for pharmaceuticals. So this industry is a key industry. And so when we look at it, we need to understand not only the principles of making these things, but understand that there are different types of electrolytic cells. And these have emerged over the years. The first one was called the Mercury Cell, then the diaphragm cell, and today the most popular and common one is the membrane cell. But before we go and look at the types of cells, I want to go through the principles of the redox reactions taking place in all of these cells, because the reactions are all the same. But we've got to understand them, be able to interpret exactly what's happening. And we've done it already to a certain extent when we looked at the electrolysis of acidified water, or even the electrolysis of salt water. And that's where we're going to start. So in all these cells, our starting point is to start with salt water. It's also called brine, and this is, we try and get it as pure as we can. The overall reaction is that we're going to dissolve the salt water in liquid water, and that liquid water produces, with the combination of salt and water, it produces for us chlorine gas, hydrogen gas, and sodium hydroxide. So hydrogen gas is a fuel, and it might actually be important more in the future. It's also used in the recycling of organic things, changing coal to oil, and so it's used by Sasol quite a lot in terms of our immediate needs. Let's break this equation down and see how it actually works. So if we go to our standard reduction potentials, we are going to need to be looking for one of those ions or materials. Starting at the top, we'll say, there's sodium. Do we have sodium? No, we have sodium ions. So we can't use that sodium. Do we have hydrogen? No, we don't. Hydrogen is one of the products. We do have water, so we're going to keep that one in mind, but know that it's not the reducing agent. We'll have to go further down to see if we can find what's going to be the reducing agent. Look here. There's a hydroxide, and it's quite high up on the table as a reducing agent. And we go even further down and we get chloride. Those are the things that we've got. So if we are clear about it, which of these pairs is going to be involved in the reaction? Well, we recognize this is going to produce water and oxygen. Well, we don't, in our overall reaction, we didn't have that. So I think we can ignore that one. But I want to just tell you a little story about what might be happening. So if we pick up in our cell, what are the anions in the cell? We recognize that there are two anions. There's the chloride ion and there's the hydroxide ion. Now, I've already said to you, we're not making any oxygen, so we can ignore this one. The other reason we can ignore this one is there's a very low concentration. The concentration of the hydroxide ion here is very low. It's 1 × 10⁻⁷ moles per decimeter cubed, whereas this is in high concentration. So because of the concentration, the chloride ion is going to be preferred. Okay? We're not going to make oxygen instead of chlorine. And you have to understand that. Even though the hydroxide ion is a better reducing agent, there's not enough of it. And so there's too little. There's more chloride ions there, we're going to get chlorine. So when we do our selection on our table, we're going to say chloride ions are going to form the chlorine gas. And if we look at that reaction, you'll see there's a loss of electrons. So that is happening at the anode. That's happening at the anode. If we write down the reaction, we're going to see that the chloride ion, and we better put 2 over there, has lost electrons. It's going to form chlorine gas plus 2 electrons. So we've got the anode reaction. Notice that it's oxidation, and we've got the anox. Very good. Now, what about the cations in the solution? What about the cations in the solution? Let's have a look and identify the cations. So in the solution, we've got sodium ions, and we've got hydrogen ions. And if we go to the table of half reactions now, we recognize sodium ions are sitting up there. They're a very weak oxidizing agent. Weak oxidizing agent. And if we go down to this point here, we recognize that we're wanting to produce hydrogen. The hydrogen's on this side. It's not where we want it. We're wanting to find the hydrogen ion, so that's not going to be that one. We have to recognize that the hydrogen ion is going to be this one here. Hydrogen ion is going to be producing hydrogen gas. But we recognize as well that there's another scenario here, and that is that we could be looking at water. Water is producing hydrogen gas and some hydroxide. And so the competition at the cathode, there are three things that could be reacting, and we have to sort out which one it is. And guys, this is a little bit tricky because we have to do some careful thinking. First thing I'm going to do is I'm going to say, let's compare the strength of the oxidizing agent. This one is much stronger. It's a strong oxidizing agent. This one is weaker, and this is the weakest. So if it was a straight choice between which one, on the strength, we would probably choose the bottom one. But the problem with the bottom one is that the hydrogen ion is a low concentration. In a neutral solution, the concentration here is 1 × 10⁻⁷ as well. And so we're going to ignore that one, even though it's strong. And we're saying, what else is going to be around the anode? Well, it's the water. And that's going to produce what we want. It's going to produce both hydrogen ions and some hydroxide ions. And we're going to use those hydroxide ions to combine with the thing that is not involved in the reaction. And what's not involved in the reaction? The sodium ions. The sodium ions do not in any way want to form sodium metal. Sodium metal is a very reactive metal. And so it doesn't want to get involved. So be very careful. This is called selective reduction. Okay? Selective reduction. We've got 3 possible things that could be reduced, and only one of them is going to work. And I hope that you understand why this cannot work. And I'll say it again, the concentration is too low. This one is too weak. You've got to be clear about that. The sodium ions are not strong enough to undergo oxidation, reduction. If they did, the sodium would immediately react with the water and produce ions again. And we don't want that sort of complication. So if we want to write down the cathode reaction, we're going to recognize the cathode reaction here is that the water is going to gain 2 electrons. And it's going to produce for us hydrogen gas and hydroxide ions. Let me just check that I've written that correctly from the table, because it's 2 water plus, yeah, I've got it absolutely right. I just must put the 2 in front of there so it's all nice and balanced. So be very clear about how to choose that reaction. It's very important. And so overall, what I want you to see as well, this hydroxide is going to be able to link up with that sodium to give us the sodium hydroxide as the other product of the reaction. So that's incredibly important. And so you can see the overall net reactions are given over here. We can add these 2 together to get the net ion reactions or ionic reactions. Overall, we're going to get 2 H2O. There's 2 electrons are going to cancel out, plus 2 Cl minus, to give us hydrogen at the cathode, and we're going to get chlorine at the anode, and there we've got the principle of how the chlor-alkali industry operates. Doesn't matter which type of cell it is, but they will use exactly the same process. Let's take a short break, and then we'll dive into comparing the different types of electrolytic cells used in the chlor-alkali industry. Welcome back from your break. Now let's dive in to our focus on the different types of cells that you find in the chlor-alkali industry. This is very important as it's an application of your knowledge on electrochemistry. So let's go and have a look. Remember, there are 3 types of cells we're looking at: the Mercury cell, the diaphragm cell, it's supposed to be a G there, and the membrane cell. So let's go and have a look at the electrolysis of sodium chloride in the mercury cell. Now, we want to be clear that the reactions that we've spoken about are exactly the same in all 3 cells, but they are slightly different technically. This Mercury cell was the first way that the chemical engineers discovered to make chlorine and sodium hydroxide. And you'll see that the problem with this is that they had to use large amounts of mercury. But let me explain, it's quite clever. So mercury, because it's a metal, can be connected to electricity. And so we have, in this place, the mercury being connected to a negative part of the battery. And over here, we have some metal rods placed into a tank which has got brine in it, the sodium chloride, and the water dissolved with the sodium comes in, sodium chloride comes in here. The chlorine, the chloride ion, gets attracted to the positive anode. What happens? Oxidation. So we've noted that. We're not going to write the equation down, but there it is. At the anode, we're getting chlorine gas. The chlorine gas is escaping. Now, the sodium ions are swimming around. They are going to be attracted to the mercury. Now, what's interesting here is that at that point, the sodium would exchange and gain an electron from the conducting mercury. But because sodium is a very dense metal, and mercury is sodium is a very has a low density, and mercury has a high density, the mercury surrounds the sodium, and so protects the sodium from the water, creates a level of separation because of the difference in densities. So in that way, sodium is captured. The sodium ions sodium ions become sodium metal. Sodium ions are captured into this magnum, or this mixture, and in a separate tank, the sodium is now and mercury are washed with water. The sodium immediately starts to react and produces hydrogen gas, and what's balanced over is the water that produces sodium hydroxide and mercury. What sinks to the bottom is mercury and some pure water. Pure water gets separated out, and the mercury carries on and pumped back into the tank, and in that way we get the whole reaction. Quite an interesting little story in terms of the way that the mercury is able to capture the sodium and prevent it from reacting and in the original container and polluting. The chlorine that was being produced up here, we wouldn't want chlorine and hydrogen to mix, because chlorine and hydrogen mix, they can explode in the presence of light. So we definitely don't want that happening. So it was quite a dangerous experiment or apparatus, but the more important thing, the biggest disadvantage, was that mercury is poisonous. And because it is poisonous, it's people that are exposed to it can get very sick, can get mental disease from it, can get ingested onto your lungs, onto your brain, absorbed by the blood vessels, and so environmentally not a good idea. And so because of the pressure and the ideas of preserving the environment, this particular cell has been largely phased out. Not a good idea to have it, but it was quite effective in producing sodium hydroxide, although the percentage of sodium hydroxide wasn't very well controlled, because the production of hydrogen, when you add sodium to water, isn't a particularly well-controlled experiment. And so the sodium hydroxide wasn't very pure, and there was a little bit of wastage as well. So it wasn't as efficient. So the two things, mercury is a poison, and it was inefficient. You weren't getting a very pure product, inefficient. Right, let's go and look at the next type of cell that we're dealing with. This was a little bit more advanced as people started to think about it a little bit better. How could we get rid of the mercury? And they came up with the idea of using a membrane. This particular membrane was called a diaphragm, and it was allowed most things to pass through, and I'll explain what I mean by that. So Again, we have an anode and a cathode, and we know that the anode, we're going to get chlorine, and at the cathode, which was the negative one, we're going to get hydrogen. So what we've got here is the chlorine coming out. This is the chlorine gas being produced. What we've got coming in is the brine. The brine is being sodium chloride and water, so it's aqueous. And we're getting the chloride ions that are going to be attracted to the positive terminal, and we're going to get that reduction, that oxidation reaction. So that is your anode. We're getting oxidation there. I'm not going to write it in full. Well, might as well write it in full. The sodium ions are going to be floating around with water, and they can all pass through. Water can filter through, sodium can filter through, and everybody is happy. What then happens is selective reduction. The sodium ions aren't involved at the negative terminal. Water is reacting over here at that terminal, and it picks up and gains electrons, and the result is we make hydrogen. So there's where your hydrogen gas is going to come through, and we're all happy. What's pumped out of the cell on a continual basis is some sodium hydroxide. So out of this reaction, we not only got sodium, but we also got hydroxide, if you remember the redox equation. The hydroxide links with the sodium, and away we go. Now, one of the problems of this diaphragm cell was that there could be some impurities. And the major thing was that this cell didn't stop chlorine from getting through. So in this mixture here, you actually got sodium hydroxide and sodium chloride. And that's quite difficult to separate. There wasn't a lot of there weren't many chloride ions going through, so it wasn't very impure. It was impure, but not so much that you couldn't use the product. But people still wanted pure caustic soda. And that was when we started to develop the new type of cell. So the disadvantage of the membrane cell was that there was impurities in the sodium hydroxide. As I've explained, that was because of the chlorine getting through. Now, the most efficient cell is the one that is called the membrane cell. And this uses new technology of being able to have membranes that are semi-selective. In other words, they allow certain ions to pass through, but they don't allow other ions to come through. And that's exactly what happens here. So into this solution, into the cell, we get a high concentration of brine. So that's a high percentage. The concentration of sodium chloride is high. High concentration. And what happens is the chlorine immediately gets attracted to that. You get the chlorine gas bubbling off, and away we go. But the extra chlorine may think it's going to drift across there, but the membrane stops it. And the only thing that can get through onto this side is sodium ions. What's left over, because this is all pumping, is depleted brine. So it's sodium chloride in the solution, but with less concentration, low concentration. Okay, over here, same thing happened as before. The sodium gets introduced here, sodium hydroxide joins up, and away, and that gets pumped into a tank. We collect it there. It gets concentrated, and it returns to the valve. Here, water is added to give you a dilute concentration, and so the process continues. And we're getting pure hydrogen being produced here. And so the key to this is that we're getting a higher concentration of sodium hydroxide. So just to wrap quickly, the advantages of here, the percentage of sodium hydroxide is greater. That's the biggest advantage. and there's less wastage. Just to revise quickly on these overall electrochemical cells, remember they transfer electrical energy into chemical potential energy. The E naught of the cell, when we calculate it, is always negative because you need an input. They're non-spontaneous. Very important. Oxidation takes place at the anode always. Reduction takes place at the cathode. And please learn that what the electrolytic cells are used for: extracting elements, electroplating, electro-refining, and of course, they're also used in the chlor-alkali industry. Well, I hope you've enjoyed this. We'll see you again soon.